All right, going back to this, it's often perhaps helpful to frame these this whole topic has been about, it's called problems, but really it's about how we go about breaking down the different pieces of the problems we're looking at and the algorithms, and how we can, once we break it down a certain way, we can think of the problem and the algorithms a certain way, which might help us make decisions effectively. When we have a problem and we are searching for admissible solutions to that problem, whether it's an optimization problem or a modeling problem, the search, we have a space of all possible solutions. And there is like a topology to this space. There is. Consider the bit string. The string 00000 is adjacent to the string 10000. Like it's or at least it's closer to the string 10000 than it is the string 11111. There is like a distance. There is like an actual like topology in space and distance between solutions. So there actually is the structure to the space, like an actual structure. And when we have an algorithm that's, if we're looking to optimize like traveling salesperson, the search space is all possible Hamiltonian cycles. Or really, it's actually all possible ordering of cities. Some orderings are going to be more similar than other orderings. We have this structure to the space. And our algorithm is some mechanism to move through that space. Now, what I'm saying here, raise your hand if you've taken machine learning or are taking machine learning right now. So I don't know if this framing was done in that course, but it works there as well. This is not an evolutionary computation thing. This is like a machine learning AI optimization thing. So, I mean, you're in it right now, you were saying? Like, you haven't talked about it in this frame of reference yet. And if you took it before? You didn't talk about it with this frame of reference, no. That's too bad, because when you frame things like this, suddenly it becomes a little easier to abstract, well, we have a problem. If we switch out the algorithm, we switch out the way that we're traversing this space. And maybe if we flip ways that we we interpret the problem, we could actually modify how the space looks. This is what I mean when I'm saying breaking the problems and the algorithms down and thinking of them this way allows us to reason about how certain modifications actually are affecting how that thing's moving, or does it affect the space, and so on. So this is actually a great way to frame these problems. It makes things a lot simpler. Now, if the search space is small enough, it's possible to enumerate all possible solutions. But like with TSP, we've got an issue of, well, there's a lot of possible solutions. And although the algorithm for finding the best solution is simple, it ain't finishing in another lifetime of the universe if you hit run today. Like, it's not going to happen. So yeah, it allows us to ask, what's a good way to traverse the space? Can we modify the search space? Can we change how it's done? Is there any feature or fact about the search space that we can exploit? Is there a gradient in the space I could take advantage of? Can the search space actually be simplified? Can we eliminate chunks of the search space? All of these things are hard to reason about if you don't have a frame of reference like this. And these are all things that we're going to want to do. So optimization versus constraints. Now, with TSP, it's easy to see it as an optimization problem, because the goal is find the smallest solution. Find the smallest Hamiltonian cycle. It's a little harder to do something like that if you have a, well, let me take a step back. A constraint would be something like n queens, 8 queens. Is it valid or not? That's a constraint. We want solutions that are valid. If we can modify n queens to be an optimization problem. Instead of looking for a valid solution, we could say like, well, start by looking for solutions that have less conflicts, less attacking queens. If there's fewer attacking queens, that's better. We want to make our way towards 0. And that actually gives us a gradient. If I have a solution, if I'm in my search space, and I have a solution that has 4 conflicts and a solution that has 2 conflicts, 2 is better. So now I have like a direction, a directionality. I can make a decision. If I'm really only thinking of it as a constraint problem, where I'm like, well, here's a solution that's not correct, and here's a solution that's not correct, which one do I go to? Which one's better? And you're like, well, I have no way to know. So this is an example of it being easy, or maybe easy is not the right term, but maybe a simple strategy for turning a constraint problem into an optimization problem. It's not always the case, though. And sometimes optimization problems can have constraints, like city X needs to be hit before city Y, or city X, Y, and Z need to be hit in some time frame or something. You can add constraints to make these problems a little bit more complex. And sometimes it's even so I gave you an example of converting a constraint problem, the n queens, to an optimization problem. But sometimes you can kind of do the reverse, where you take an optimization problem, but you add some constraints such that the search space can become smaller. So a quick and easy example of this is the search space salesperson problem is really, it's any ordering of cities. But the reality is, with TSP, you want to hit each city once and only once, except for the first city, which you start at and you end at. So it would be silly to include in the search space a path that says go to city 1, go to city 2, go back to city 1, go back to city 2, and bounce back and forth. We could constrain this search space by saying, no, you're only allowed to visit each city once. Because a correct solution would only have each city visiting once. So eliminate all of those extra possible solutions. You constrain the search space. Suddenly the search space is a lot smaller. And we'll sink our teeth into this a little bit more a little later. And now hardness. Who here took theory of computing? Only one person. All right. So of course, you're familiar with hardness. Okay, if you haven't taken theory of computing, and I say, if I were to ask you to give me a solid definition of what is NP hard and NP complete, would you be able to give me an answer?
I think it's like whether it's like exponential time or not.
It's going to be it's along those lines, to put it simply. I'm going to summarize all that. A problem is easy if we have a way to solve it quickly. A problem is hard if we don't. And when I say no fast solver, I mean like, oh, the solver will take, to find the optimal solution, the solver will take longer than the universe has existed. Right? That's what I mean. A fast solver could be something that takes a week in the context of this type of stuff. Now, NP hard and NP complete, I might have some pictures down here. I do, perfect. I will talk about it a little bit. All right. Before I jump to that, then, let's make our way. Continuous versus discrete. Some problems are continuous. They might have real values. And this is called numerical optimization. These problems have an uncountably infinite search space. And just to make sure everyone is aware of what that means is, I need everyone to answer. I'm going to quiz you right now. This is a big, tough question. What comes after 1? 2. Nailed it. What comes after 2? Come on, wake up. What comes after 100? What comes after 1 billion? Yeah, you're nailing it. So far, so good. Great. Okay, cool. I'm going to change the question slightly, and I'm going to ask you again. You were dealing with integers there. Now I want to go to real numbers, with decimals and stuff. What comes after 1? Well, you skip some.
1 plus x as x approaches 0.
Nice try. What did you say comes after 1? 1.1? Yeah. But you missed 1.01, which of course misses 1.001. Real numbers suck. There's actually, for those of you that don't know, there's actually multiple different types of infinity. Integers are what we call countably infinite. There's a lot of them, but I can keep going. I can put my finger on each one as I go. Real numbers, we're in trouble. There's a lot of them. I mean, there's infinite in the sense, in the same way like integers, you know, it keeps going. But also there's like an infinite number of numbers between 1 and 2. Hell, there's an infinite number of numbers between 1 and 0.1. And so on and so on. I mean, we've got an issue. It's infinity, but it's like worse, right? It's like infinity in multiple ways. So this is what we would call uncountably infinite. It's worse. They're both infinity, but one of those infinities is bigger, right? Raise your hand if you've learned this before. A couple people, okay. This is also the same reason computers suck at floating point numbers. There's only so many values that the computer can represent with 64 bits, traditionally speaking. So there is a max int that Java is happy with, right? Because there's a finite number of them. Well, if there's a finite number of integers, there's going to be a finite number of floating point numbers. And so that's where floating point precision comes in, is the computer goes, good enough. We just hacked it until it was good enough, and then we said, good enough is good enough. Real numbers suck. When you have a problem, like I said, okay, if you have a small enough search space, you can enumerate all problems. If you have a continuous search space, it's not possible. You're screwed. It's not possible. If the problem is defined in terms of discrete values, like integers, then it's called, well, it could be numerical, but it could be combinatorial optimization. So what to know about hardness? So this is what I was talking about a moment ago, easy versus hard. Easy is we've got a quick solver for it, where quick is relative. And then hard is we don't have a quick solver for it. There are problems that are class P. That means all of these problems are framed as decision problems, but we could kind of ignore what that means. A decision problem would be like yes or no. But we could ignore that detail to get the gist of what's going on here. We have class P. These are problems that can be solved in polynomial time. It might be a terrible algorithm. It might be n cubed. But it's still polynomial time. And be careful when talking about these things, because we would say like it can be solved in polynomial time. It can be solved by an algorithm in polynomial time. Then there are NP. These are NP problems with positive solutions that can be verified in polynomial time. But maybe we can't solve them in polynomial time. But maybe if we have one where it's like, yep, that's correct. I somehow have a magic, I come up with a solution. I have an algorithm that gave me a solution. And I give that to some person who's standing there like this. And they look at the solution and they say, that is correct. And they can do it because they verify this. It's possible to verify the solution in polynomial time. This would be an example, a restricted subset sum. Does there exist a subset of a set of integers that sums to 0? If I gave you a set of integers and I asked, is there a subset in here that sums to 0? This is a very hard problem. But if you gave me a solution that said, yep, here is my solution that does sum to 0, I can look at it and calculate it pretty easily, right? Basically, you give me a collection of integers and I add them together, does it add to 0? I can do that in polynomial time. Then there's NP complete. These are decision problems with no known polynomial time algorithm, but can be verified. Oh, pardon me, class NP. The polynomial time, I mixed up a little bit there, but let's go on with NP complete. There's no known polynomial time algorithm, but can be verified in polynomial time. And what's interesting about NP complete problems is if I gave you a problem that is classified as NP complete, is it's actually equivalent to all other possible problems that are also NP complete. If you have a problem that's NP complete and you have a problem that's NP complete, they're actually the same problem. You can reduce them to one another. They are equivalent. Yeah?
What's the definition of polynomial time?
That would be like an algorithm that's like n squared. N to the power of 5 is even. But as soon as you start seeing things like exponential or factorial in your complexity, oh no, you're screwed. And then there's NP hard. These are the real big tough ones. These are decision problems with no known polynomial time algorithm, and you can't verify them in polynomial time. For example, the decision version of TSP. I'm not sure if that's right. I might have the optimization. I need to go double check that. I feel like that's wrong. I feel like it's the optimization version. I guess it would be the decision version. Yeah, okay, yes, this is correct. Decision version of TSP. Traveling salesperson problem, there's no known polynomial time algorithm to find the best solution. Best we have are some heuristics that'll run in polynomial time, but there's no guarantee of optimality. If you gave me a solution and it was, is this the optimal solution? I would go, I don't know. No one knows. Now on the assignment, the instances I give you actually all have, I believe they all have a known optimal, which is shocking to me. But once you get these extra hard problems, which you can find other hard problems out there, you'll find tables online of the best known solutions, but no claim on that solution being the optimal solution. And those tables will update every once in a while until somebody comes along and says, I found a better one here, look. We can verify that it is a correct solution with the total distance of whatnot, but we can't confirm if it's the optimal or not. All of this is to say, what we really care about for hardness is there are some very hard problems out there. And a lot of times when it comes to these hard problems, maybe even having the idea of I want the optimal isn't even a valid question. Maybe it is a valid question, but we have no chance of getting it. So this is where we go, well, a really good solution will work. It'll be fine. If I'm a traveling salesperson and I have to visit 100 cities, I'm not finding the optimal solution anytime soon. But if someone gives me a pretty damn good solution, I'll be happy, right? If it saves me extra bucks in gas, I'm really happy. And then if tomorrow someone shows up with a better one, even better. But it doesn't have to be the optimal. It just has to be, I would love the optimal. But if it's good enough, it's good enough. Think of a machine learning algorithm learning to walk, right? It's learning to walk. Does it learn the best possible way to walk? Probably not. It just needs to walk. In the same way all of you. How many of you have tripped recently? Yeah, so you're terrible at walking. You clearly don't have the optimal configuration of walking in your brain somehow encoded. No. But did that matter? No. Maybe there isn't even such thing. Maybe even saying the optimal way to walk is a stupid statement. Maybe that's not even a reasonable thing to ask or say. For these types of problems, this is where we're using things like evolutionary computing. Optimizing a bit string, yeah, we're not using GAs for that. That was a silly toy problem. Hard problems, yeah, that's where we're using these things. We use these algorithms when we go, I don't know what else to do. These are the last type of algorithms you resort to. These algorithms are in the realm of what we call computational intelligence. Okay? If you were to take a line on what you want to do in machine learning and what you sometimes have to do, what you want to do in machine learning is not even have to do machine learning. You want to be able to just look at the data and find your trends. Then maybe if that doesn't work, maybe you resort to some form of regression analysis. You know, can I draw some straight lines? Yay. If not, okay, maybe you resort to like k nearest neighbors, right? Something simple. We want simple. Now, mind you, as computer scientists, often we don't. We want the most complex, sophisticated solution available because we just love that shit. But in reality, we want the simplest one. You know, if k nearest neighbor doesn't work, maybe I try like decision trees or gradient boosting or something. Only when I'm out of all other options will I jump to something like neural networks or evolutionary computing. I don't want to use these algorithms. These algorithms are terrible. These algorithms suck. They take so much time to run. They are computationally very expensive. Therefore, they're actually kind of bad for the environment when you think about it. They're using all this electricity. There's a lot of time wasted on solutions we know are absolute garbage, but we at least can see that the garbage solutions are important for the evolutionary search. They take forever. They're notorious for overfitting. We don't know, like there's no guarantee on correctness. There's no guarantee on these algorithms will even converge. There's a lot of reasons to hate these algorithms, but sometimes that's all we've got. Sometimes we just go throw a neural network at it and hope for the best. Sometimes, I don't know, can we use particle swarm optimization for this problem? I don't know, maybe. Sometimes it's all we've got. The moral of the story here is you don't want to use these algorithms. Why are you even taking this class? You don't want to learn this stuff. This is the last stuff you want to use. But sometimes it's all we got. Sometimes we don't really have another choice. This is like, I'm all out of options, let's throw this shit at it and hope it sticks. Sometimes it does, sometimes it doesn't. Any questions about that? The point is, we use this for hard problems where we go, I don't know what else to do. One thing that's nice about evolutionary computation is, and other forms of similar machine learning, is when I say, I don't know what else to do, there may exist somebody out there that does know what to do. But I don't need to, and the reason they know what to do is because they dedicated a decade and a half to understanding everything about TSP, for example. But I didn't. I can whip up a GA in 20 minutes to do it though. Good enough, right? So not knowing what to do doesn't mean just for everybody, it means for me. There might be a better way to do it, but I also don't even need that much specialized knowledge about TSP to get a damn good solution with a GA. It's kind of a nice thing about it. Any questions? So the origin. So, okay, look. All of this obviously has been tied to what's observed in nature. The focus of the terminology, and a lot of this comes from biology, but as I've said already in the course, all of these principles aren't biological principles. They are principles of everything in this universe. Everything is subject to evolution and evolutionary processes. There's chairs here. Chair's a bad example. If I go outside and there's a rock on the ground and someone goes, why is that rock there? The best I can say is because it's not there. Because it's not there, pardon me. Why is it there? Think of all the weird, funny little things that ever happened to put a rock somewhere, right? Why is it there? Why is it that size? What happened to it? Think of the billions of years that rock's been around probably, right? Maybe millions, I don't know, depending on the rock. A bunch of weird stuff happened and it just kind of showed up there. And why is it there? Because it's there. But why isn't it over there? Because it's not. Why does it exist? Because those particles stuck together and they were subject to that at one point in time in the history of its existence, right? Everything. Why does this university operate the way it does? Because it was set up once and it's kind of like settled and does what it does. Why are businesses set up in such a way? Why do some businesses survive and some don't? All of these things follow these evolutionary processes. But the inspiration from biology, okay, we've got this like last universal common ancestor. Life began somehow, we don't fucking know. But it started. And since then, it's been great, right? We're just chilling. And there's a whole bunch of different types. You know, we got eukaryotes, bacteria, archaea, K. I don't even know what that middle one is, but it exists, right? There's a lot going on, and it all came from somewhere. And all of this is a consequence of just things changing, environmental factors affecting them. All of that came from one thing eventually, though, as far as we know. Isn't that weird? One thing we would look at and classify as living was the origin of, there was a last universal common ancestor, as far as we know. And everything, we are just as related to that as the bacteria on my hand, right? Isn't that nuts? It's crazy. And this all happened through the same processes we're talking about here. Random changes and environmental factors that may or may not kill something off, and random changes may or may not have some benefit within that environment, but at the end of the day, after all these processes, mechanisms for existing or persisting, reproduction, ability to have offspring, pass on traits, thereby keeping your DNA existing. All of that happened, and here we are. Crazy, right? The power of evolution is obviously evident just in the sheer fact when you look at the diversity of things on Earth. And the environment is filled with populations of individuals that strive for persistence, to survive and reproduce. If I survive, I persist. My DNA persists. But eventually I'm going to die. But if I have the ability to reproduce, my DNA can also kind of persist in my children, right? So that's a good thing. Or if it's asexual reproduction, whatever, I just reproduce and I'm making copies. Those copies might be different every now and then, just mutations and whatnot, but the fitness of an individual. Oh, and also I want to make sure I'm being clear. When I say a population, I mean when you look in the environment and you say there's a population, I don't just mean like a population of humans. I mean the environment is made up of everything in that environment, right? So the population includes things like dogs and bears, right? Now, I'm not reproducing with bears, but we are in the same environment, and maybe we're competing for the same resources.
Does it only count living things?
Pardon?
Does you only count living things?
Well, not really, because the environment is the constraint. In fact, it's kind of funny. Because the population and the environment, a population is within the environment, but the population itself is also a part of the environment. So the environment, in reality, is just like our environment, everything in it. Everything I'm competing with for existing, there's a lot of like bacteria that'll F me up if I didn't have systems in place to keep me alive, right? That bacteria, those viruses, they want my resources so they can survive, right? But I want my resources so I can continue to survive. Everything is like this. And the fitness, so the word fitness has a special meaning in biology. I think I'll give you the proper word or the proper definition in a moment, but it's like the ability for that thing to persist and reproduce. So the fitness is determined by the individual's interactions with the environment and other individuals, which is again perhaps, like I just say, other individuals are, though, really just part of the environment itself. But, it's kind of funny. With evolutionary computation, populations of candidate solutions are evolved. The fitness of the candidate solution is a measure of how good it is at addressing the problem at hand. The problem, or like the search space, is the environment that the population is in. So now I'm just drawing the comparisons. And the candidate solution's fitness dictates its probability of survival or reproduction, right? Because fitness is what selection uses for determining who to pick. Reproduction creates imperfect copies of individuals. You're never going to get perfect copy. Well, you might get a perfect copy, you might not. Asexual reproduction there could be things that happen where you don't get a perfect copy. Sexual reproduction, well, you're not getting perfect copies anyways, because that's not how it works. But even the two halves aren't going to be perfect copies because things will just change. It happens. Sexual reproduction incorporates genetic information from both parents. Mutation occurs in both sexual and asexual reproduction, happens all the time. And sometimes these changes are harmful. Sometimes these changes are neutral, they don't do anything. And sometimes these changes are beneficial. But there is nothing, I'm using these words harmful, neutral, and beneficial, as if they have some gotta make sure I'm being clear on this. I'm using these words not as a judgment like, oh, that is bad, that is good. I'm not using these words. I mean how, all in the context of its ability to survive and persist within the population. I'm not making any judgment. It's just the environment, and it's just the population. Sometimes the changes are harmful, and harmful could be kind of negligible, or maybe really catastrophically problematic for the organism. Maybe even some changes are neutral, but maybe something changes in the environment that neutral change actually becomes bad. Or maybe it becomes good. All of this is there is no intelligence involved in any of this. It's just shit changes, and how did those changes make a difference as for its existence within the population? Maybe it moved its environment. Suddenly that change was a good thing or a bad thing. It's all willy-nilly. It's crazy. Sometimes these changes are beneficial. Again, beneficial might be something along the lines of, maybe my ear was slightly bigger and I could hear better. Therefore, I heard the lion coming earlier. I don't know. But that's talking about evolutionary processes as if it's happening at that type of a time frame. No. A lot of changes are benign. A lot of changes are bad. Some changes are good. But it's interesting. There was this concept, I was listening to a podcast. I don't even remember who it was and who they were talking to. But basically, it doesn't, how did they word it? I thought it was really interesting, and of course, I can't remember how they worded it. I'm going to do my best. Bad changes, a trait of a population, and remember, these are like population-based things, right? Sometimes changes are harmful. We could talk about this on the individual level or population level, because some change can affect a population, right? If you've got a bunch of turtles living in a pond that's fairly isolated, they might develop some minor little changes. That doesn't really mean anything, but the changes will affect a population. Negative changes don't take long to disappear. Positive changes take forever to happen. Because there's no one going, that was good, do that more. No, there's no force like that acting on it. It's just the creature doing its thing. And if some of the changes affected its ability to do its thing in its environment in a good way or a bad way, that's it. Competition. So given that, the environment does have limited resources. There is a limited set of resources within any environment. And individuals are often, we have this intrinsic interest in existing. If we didn't have this intrinsic interest in persisting, we probably wouldn't be persisting. Living things like to be alive. If we didn't, we wouldn't be alive. Do you agree? Right. So there's something about us. We've got this desire to want to exist. There's a limited amount of resources. Competition is going to happen. Why are humans so aggressive and hate each other and so competitive? It's in our blood. We've had millions of years of evolution. When we were part of that last universal common ancestor, I don't just mean as humans we learned to become competitive. No, everything is like, screw you, I'm out for me. That's the strategy. Obviously, now we could hit pause on this, and this is where we can start to have a fun conversation about how evolution happens in layers of abstraction in different dimensions. So we have our existence, our physical world. We have our biological evolution, right? And we as like a society, we have formed like a culture and a society, and we have norms on how we interact with one another. And those evolve over time as well. I mean, the way we interact with one another 100 years ago was different than it is today. Same with 500 years ago, right? So all of these things evolve and change. At the end of the day, so back to that is, obviously, so you could ask the question, why do there exist social animals? Why are some animals social? Well, there must have been like a tipping point for that species. I mean, let's think about this rationally. Let's use our intuition. Some species are not very social at all. They hate each other all the time, right? Humans, in spite of everything we know about how much we hate each other most of the time, we still are relatively social, right? We live and work in close proximity and, you know, we play nice. And why do we do that? Well, there must have been an advantage. This might be a really good way to introduce one of the ideas of evolutionary thinking here. You got to remember, let's say you had, I don't know, 700,000 years ago, you had two tribes of humans. I don't know. One was very nomadic, and they hated each other. This is going to be I'm going to try to come up with a good example, but some of this you just kind of have to think about and figure out. But I'm going to try my best to communicate these ideas. So bear with me as I try to articulate this on the fly. We could talk about this in terms of selection pressure. Remember that idea of selection pressure in the GA? Selection pressure is something is kind of high, something with a high selection pressure is somehow, for some reason, it's good. And that it has like the self-feedback, right? A change happened, it gets selected for more, therefore that change is going to be bigger, it's going to get reinforced and whatnot. So there are non-social animals and social animals. There would have been a point where humans evolved the ability to be social. And when you look at society today, we have made it to where we are while being remarkably social, right? We are a very social species for hundreds of thousands of years. We've been living and chilling, right? So why? Why did we become social? Well, probably because that's what enabled us to kind of take over this planet. If we weren't social, if we evolved to not be social and develop culture and formal rules of how we interact with each other and all this nonsense, if we didn't do that, would I be here today talking about this? And I don't just mean because I wouldn't be able to get you all in the same room when we hate each other. I mean, would humans have survived as a species? Is there like a really high fitness value associated with being social? Forming these complex relationships? Right? And this social aspect is not just a human thing. There's a lot of creatures out there that are like this too, right? Obviously. So clearly, am I kind of communicating a point? Like, do you kind of see what I'm saying is, why are we social? Well, because we are. Why are we not social? Well, maybe because, hell, we even have word for like antisocial people, right? They're like sociopaths, right? Like, they are so the other. Is that a bad thing though? Well, maybe it's in conflict with, I don't know. But the point is, there was a point in our history where clearly it was a good thing to be cool to one another, right? I don't know if, I'm seeing a lot of blank faces, so I'm not sure if I'm getting a point across. But just maybe think on this a little bit. All right. Individual versus population. I kind of mentioned this a moment ago. The idea of diversity and competition exists within a population. So there are two big competing factors, diversity and competition. Those are two important, powerful things that when put against each other emergence can happen, as in like evolution. Diversity exists and competition exists within a population. And it's often helpful to think of the population evolving instead of just individuals. Obviously, the individuals are what's changing, but sometimes it's better to take the step back and look at the population. The changes are happening there. And when you look at that average population, remember those curves? Which curve was at least more fun to look at? The max was often like, and the average was kind of like maybe a little like this, right? That's what's changing. The individuals in there are obviously changing, but it's good to think of the population in aggregate. Having a balance between competition and diversity is very important for populations. Having too much competition will often lower diversity. Having too little diversity can limit the population's ability to adapt to changes, or at least adapt to the environment. And having too little competition can increase diversity, but having too much diversity can stagnate any specialization within the population. If there's having too much diversity in the population, well, where's that guiding force? You need diversity and you need competition. That's where all the magic is happening in the GA. Fitness and selection is for like the competition, and then diversity is with the genetic operators. That's the magic. I saw a hand. Yeah.
So like changing the environment would be like changing the search space.
Yeah.
Right?
Yeah.
So like, is there any like algorithms where you would actually like change the search space like halfway through or something like that?
Yeah, there actually is. Now, but those are particularly like funny little cases.
Yeah.
But let's think about, we could think of this like as an our environment, right? And how the environment changes, right? And how we have to adapt to changes in that environment. You can even think of it at different scales too. You can think of like even like a change of seasons. Or you could think of like a change in climate, right? Well, how are we going to adapt to that, right? Yeah. So if we don't have enough diversity and we're all really focused on one thing, we might not be very good at going like, hold on, we need to figure something out here. Where if we have an increase of diversity of like ideas and whatnot, then we can be like, well, okay, we need to figure this shit out. We're, just another example of these two things being at odds. But the fact that they're at odds is almost critically important in the first place. Systems. So, populations of living things evolve, but a population of living things is just a system. And a system exists within some environment, which in itself is a system. And a population is made up of individuals, which are themselves systems. And each individual is made up of many more systems. And each of those smaller systems is made up of even more systems, right? So, I mean, we could play this game forever. We could keep going. And there's the phrase, like it's turtles all the way down, right? What's the universe made on? Well, it's like on turtles. And what's below that turtle? That's another turtle, right? So there are systems everywhere at different scales in aggregate. I'm not just talking like, oh, okay, within me there are systems. I have like a nervous system. I have a hormone system. I have a bunch of cells that are doing things. I have different types of cells that are doing things, that are interacting with one another, that make up systems in and of themselves. I have a circulatory system. Within there's the cells, and then there's the particles really within this. There's the way the proteins are interacting. We could play this game forever until we get down to subatomic particles, and then, I don't know, maybe that's the end of it. Or maybe there's more, I don't know. Point is, no matter where you look, you can draw lines around a system. And each of these systems is subject to change. And there's going to be some pressure for existing, whether the system exists or not. Living things have an intrinsic interest in surviving. But when you look at a business wants to survive. If it didn't care about surviving, if a business didn't care about making money and surviving, would it last very long? No, it would die out. right? So it's not just living things that have an interest in existing. If something exists, chances are, when I say it doesn't not want to exist, that like imposes some intelligence on the thing. But like, if circulatory systems didn't exist, well, neither would you. Neither would any of us. So good thing it exists. Does it want to exist? It doesn't want to exist, but if it didn't exist, we wouldn't have it. I know it might sound like, I want to make sure, I know it sounds like I'm saying like stupidly true statements as if they're profound. But it actually is. You need to make sure you're taking the time to think about these things and realize that like, actually, okay, these kind of are, I've never thought about it this way. And it is kind of a big deal. Systems evolve, not just biological systems. Don't put life on a pedestal. It's not that special. It's just another system within the universe, in the universe, which make up bigger systems and are made up of smaller systems and are subject to other systems that we only have to interact with. All that is really needed is a mechanism for change and persisting. Systems evolve as a consequence with its relationship with its environment, and its environment, of course, is also including its population that it exists with. Sometimes the environment might have some intention behind it. Sometimes it's aimless. But if you have an aimless environment, if it didn't exist, well, maybe all of these ideas will become a little bit more clear once we get to the next subsection. But we won't have time for that today, so we'll stop here. Does anyone have any questions? Okie dokie. All right. See you all whenever we have class next.